In this video lecture, we're going to cover naive Bayes, but before we dive into what it is and how it's helpful, we're going to first look at three different kinds of probabilities using our tennis dataset. So we know that the tennis dataset is currently composed of 14 data points, and the idea here is that you have 4 attributes, which are outlook, temperature, humidity, and windy, and you're sort of trying to predict a target here. So predict the target or your class, which is whether or not you're going to play tennis. So the first probability, I'm going to start off, is the marginal probability. So marginal probability. And again, the probability is basically the likelihood of an event occurring. So I could say that the marginal probability here is just going to be the probability that the outlook was sunny. And to compute that, you're going to basically count how many events were there in your data set, your historical data set here, where the outlook was in fact sunny. So you're going to have 1, 2, 3, 4, and 5 here. And you're going to divide that by the total data points, which is in fact 14 here. And that roughly estimates to 0.357, let's say. I can also calculate the probability of the event that the outlook was in fact overcast. And in that case, you're just going to count how many overcasts there were. 1, 2, 3, 4. 4 over 15. And that gives you roughly 0.286. And finally, when the outlook is rainy, and that's going to be 1, 2, 3, 4, 5 over 14. So it's roughly 2.357. So here I'm still not checking whether or not they're going to play tennis or not. Here I'm just right now calculating the marginal probabilities that the outlook is in fact sunny or that it is overcast and rainy. Now, a few things to note here is that probability, either of these, is always going to remain between 0 and 1. So they're not going to exceed 0, 1, and they're not going to go beyond 0 here. And also the fact that for a single outcome here, for a single, let's say, attribute here, I can sum up the probabilities of all of the events happening, and that's going to add up to 1 here too. We can also think of each attribute here as a random variable whose value is governed by a probability distribution. So basically think of having a degree of belief that the variable will take on a specific value. So if the probability here is 0.357, so it is greater than at least zeros, you're going to say that, okay, there is a chance that the outlook might be sunny based on this data set here. Another thing to note is that in the tennis data set, all of these are basically discrete categorical values, but sometimes in our data set we also have numerical variables. And so for those, you're not just going to look at the discrete probability distributions. Instead, you're going to look at continuous distributions, and the famous one we know of is the normal distribution. I'm just going to write it here. And it is given as the probability of x is going to be 1 over square root of 2 pi sigma squared e to the negative 1/2 of x minus mu squared over sigma squared. So again, where this is your standard deviation, x is your value that you're finding the probability for, and this mu is your mean. Now with machine learning, we are usually interested in more than one random variable at a time, so we might not just be interested in, what was the event that the outlook was sunny. In fact, we might be more interested in saying, what's the probability that the outlook was sunny, and let's say that the humidity was high. So in that case, we're going to bring in our second kind of probability here, and that is called a joint probability. In that case, I will say that the probability of outlook is sunny, and, so this comma designates an and the humidity is high. So we're also able to compute joint probabilities here. So what was the probability of the event that outlook was sunny and that the humidity was high? And to be able to solve that, we're going to build up a table actually. So we're in fact going to look at our humidity and our outlook. And for each of their values, we're sort of going to build up a table based on our data here. And so we know that the outlook has the values sunny, overcast, and rainy here. And then we know that humidity will take on the values of high and normal. And so what we'll do is we're going to basically count the probabilities separately for when outlook was sunny and humidity was high, then outlook was sunny and humidity was normal, and so on and so forth. So to do that, we're going to find all the sunnies. So let's change a color here and go 1, 2, 3, 4, 5 here. And then for which humidity was also high, so 1, 2, 3 here. And so we're going to have 3 over, again, the total number of attributes, so 14. And for normal, it's going to be the remaining 2, I think. So you'll have normal 1 and then normal 2 here. So 2 over 14. And similarly, you're going to then find how many data points you had where the outlook was overcast and the humidity was high. So 1, 2, 3, 4 overcast, of which we have 1 high, 2 high, and then the other 2 are normal. And then same thing for rainy, so 1, 2, 3, 4, 5 data points. We're going to say 1 high and 2 high here. So 2, and then the remaining 3 are going to come over here, so 3 over 14. So once you have made this table here, you can finally answer questions like, what is the probability that the outlook is sunny and that the humidity is high? Well, you're going to say, okay, sunny over here, humidity high. So that's basically what we're looking for. And you'll say that the probability of those 2 events occurring at the same time is 3 over 14. Now, a couple of things to note here is that if I were to sum the probabilities across here in that direction, you're going to end up with the marginal probability of the outlook being sunny. So we know that the probability of outlook being sunny is 5 over 14, and if you add these 2 together, you're going to get 5 over 14. Similarly, for rainy, you're going to combine these 2, and you're going to get 5/14 again. You can also sum things down the line. So in this direction, you'll have 214 plus 214 plus 315, 3/14, and you're going to end up with 7 over 14, which is the probability of when humidity is normal. And we can test that by counting how many normals there are. So 1, 2, 3, 4, 5, 6, 7, and divide that by 14, and that's what you get here too. Another thing to note is that if I were to increase the number of attributes or variables going in here, so let's say I said, okay, what if I add here that the windy is going to be equals to false here too. So now my question is, what is the probability that the outlook is sunny and that windy is false and that humidity is high? Right off the bat, you'll notice that you're going to have to make a much more complex table than just this 2 by 3 here. And so the number of values we need to model a joint probability distribution is going to grow quicker as we add more variables here. Finally, we'll also talk about conditional probabilities, and the idea behind conditional probabilities is that maybe one event is actually depending on another. So let's focus on the rainy outlook here. So I have rainy 2, 3, 4, 5 here, and the temperatures in that case are never going to be hot. So the temperature was never hot. It was either cool or mild. So you could say that whenever the outlook is rainy, based on my data set, the temperature was never hot. So it turns out that knowing something about one random variable, outlook in this case, can change your belief on another random variable like temperature. So as an example, if I were to say that there is a person and they are 7 feet 2 inches tall, you're going to already have a change in your belief, and you might think that they may weigh more than 200 pounds. And I'll know that these two, weight and height, are two independent variables. So maybe prior knowledge of one variable does impact our belief, or a change of belief basically, about the other variable here. So in that case, if that is going to be the case that we want to check the probability of one thing based on some evidence of another event occurring, in that case we will use our third type of probability, which is a conditional probability. And it somewhat is given like this: the probability of A given B. This is a pipe sign, and the way I'll read it out is, again, the probability of A given B here. And it'll turn out that conditional probability is nicely related to joint probability, because probability of A given B is in fact the joint probability of A and B divided by the probability of B here. And if I were to label things again, just to make things clear one last time, that this is a conditional probability. Here you have a joint probability. And finally, you have a marginal probability, just the probability of B itself. So we can use an example here and say, okay, what is the probability that it is going to be, the outlook is going to be sunny, given that the humidity is high? Well, in that case, based on this formula, you're going to say, okay, that is equals to the probability that it is going to be sunny and that the humidity is high, divided by the marginal probability that the humidity is high. So in that case, you're going to go and build that table for the joint probabilities, and I'll just tell you that this will turn out to be 3/14 here, and then the probability of humidity being high is just 1, 2, 3, 4, 5, 6, 7/14, and the whole thing will evaluate to roughly 0.429. So this is the probability of your outlook being sunny, given that the humidity was already high. Now, given the prior knowledge that it's going to take a lot of probabilities to compute the table for finding the joint probabilities here, let's try to come up with a way where we have a formula for finding conditional probabilities without actually using joint probabilities, and that's where Bayes' rule comes in. And naive Bayes is basically applied on top of it. So we know right now that the probability of, let's say, B given A is probability of B and A divided by the probability of A, so the marginal probability of A. Well, with joint probabilities, it doesn't really matter what comes first. You're basically combining the two probabilities together. So I could rewrite this as the probability of A and B divided by the probability of A. And I'm going to have a sidebar here where we sort of compute this thing, where I say that probability of A given B is, based on the formula, the probability of A and B, so the joint probability, divided by the marginal probability of B. And if I were to multiply both sides by the probability of B, which we're going to end up with is probability of A and B is equals to the probability of A given B times the probability of B. Now I'm going to take this value of A and B, and plug it in here. So you're going to end up with the probability of B given A is in fact the probability of A given B times the probability of B divided by the probability of A. And that is Bayes' rule. The idea that we can sort of flip the conditionality and come up with a way to find B given A using A given B, and not just those pesky joint probabilities. I want to add a little side note before we continue and apply what naive Bayes is and how to use it with the Bayes rule. I'll note that if there comes out to be no relation between, let's say, my random variables, so let's say I have a random variable A and B, and if there is no relation between them, so they are independent of each other, then their joint probability is just always going to be the product of their marginal probability. So independence here, so me saying that A and B are independent, independence here is going to be really, really important. That's the product times is going to be really, really important in trying to get rid of these joint probabilities. Instead, play around with just either conditional probabilities or marginal probabilities. And if I were to add conditionality here, I could also say that probability of A and B given some probability C is going to be, again, only if A and B are independent. It's going to be the probability of A given C times the probability of B given C. And again, this is a way to get around those joint probability distributions. Now, we know that in the real world, many things aren't really independent, and there's going to be lots of small correlations going on in there. So we're just going to pretend that they are conditionally independent, and that's going to make our math and our computation really, really easy. And that's basically the idea of the naive Bayes. So let's start by rewriting naive Bayes with our classification and our variables here. So I'm going to say that the probability of me playing tennis, given that the outlook is sunny, based on Bayes' rule, is going to be the probability of it being sunny given that I'm going to play tennis times the probability of me playing tennis. Everything will be divided by the probability of it being sunny. So I can rewrite this too in generalized terms, and I can say that this is going to be whatever class I'm predicting given some data is going to be the probability of my data given the class. So what is the probability that it is going to be sunny given that I'm going to play tennis times the probability of my class, so it could be playing tennis or not playing tennis, divided by the probability of my data here. And let me label a few things. So this here is my likelihood. this is prior, and it's basically coming from the prior data set. So the data set you're training your model on, you can definitely calculate what's the probability of you playing tennis or not playing tennis for the entire data set. And this is going to be the evidence. And again, the evidence based on your data set, your training data, let's say, is never going to change. So if I was trying to predict if I'm going to play tennis or not going to play tennis, the probability of the data or the probability of it being sunny is not going to change based on what I'm picking. And by that, what I mean is that if I were to do this, if I were to say don't play, so the opposite of this guy, and given that it is sunny, is going to be equals to the probability of it being sunny given that I don't play times the probability of not playing tennis divided by the probability of it being sunny. So you'll notice right away that the only thing that did not change is the evidence here. And so the evidence, again, is sort of a normalizing factor in this formula because it does not change if I were to change this class here. If I were trying to predict tennis, I would still divide by the probability of sunny. If I were to try to predict the probability of not playing tennis, I would still be dividing by this evidence here. So it turns out to be a normalizing factor. And if we're looking to do easy computations, we're actually going to ignore the evidence here because it's going to be the same no matter what you're doing. It's just calculated for your entire training data set. So in that case, the formula is going to change a little bit here. We're going to instead say that the probability of class given some data is going to just now be, or let me just do approximately, is going to be the probability of the data given your class that you're labeling times the probability of the class itself. And what's going to happen here is that, say I was trying to predict my data was sunny, right? I was trying to predict if it was sunny or not, and based on that, whether or not I play tennis, which will give me outlook is sunny, and I play, and the probability of me playing, and the other one, which would be not play, given it is sunny outside, it's going to look like the probability that it was sunny given that I don't play times the probability of me playing. So this is what we wanted to figure out at the whole time, right? What is the probability that I'm going to play or not play tennis given that the outlook is sunny? And so if I were to plug in these values, I will get two different probabilities here. And let's say the probability that this came out to be 0.49, that is the probability that I'm not going to play given sunny, and I'm going to plug in these values. And in the other way, if I were to compute all of these, let's say, and I'm going to put a random value here, but let's say this came out to be 0.59. So now you're saying that the probability that I am going to play given that the outlook is sunny is 0.59, and the probability that I'm not going to play given it's sunny is 0.49. And in that case, when you have the two probabilities for your two classes, it could be multi-class, you'll have multiple probabilities going down the line, you're going to pick out the best one, and you're going to say, okay, well, if the outlook is sunny, then I'm going to play tennis. So this is the one you're going to pick. And just like we talked about earlier, we're not really focused or interested in finding if I'm going to play or not play tennis based on just one single event. So in that case, we're going to have multiple attributes going on. But then when I do that, the likelihood term, so this guy here, the likelihood term, is going to turn into a joint distribution. So if I were to then say what is the probability that I'm going to play, what is the probability of my class, given that let's say that the outlook was sunny and then the windy was true, the humidity was high, what's going to happen here? So in that case, this whole thing is going to turn into a giant joint probability again. So I'm going to rewrite this here, and it's going to look like the probability that it was going to be sunny, and so joint, that windy was true, so it was going to be windy, and that the humidity was high given that I play tennis. And again, we have those pesky joint probability distribution here again, and it's going to cause issues because you're going to be calculating a lot of probabilities to just solve this equation for the likelihood here. So how do we get around the joint probabilities? Well, we're going to use our conditional probabilities, and I wrote that formula earlier when I said that if A and B are conditionally independent, if this is the case, then the probability of A and B given some C is actually the product of those probabilities, because they're not really dependent on each other. We're assuming that they are independent. And so now, using this idea here, using this notion that all of the sunny, the true, so all of the outlooks, the temperatures, the humidities, and the windies, all of them are independent of each other, we can sort of easily compute what the probability of playing and not playing is going to be. And by that, I mean that the probability of me playing tennis, given, I'm going to use these, so given that the outlook was sunny, given that the humidity was high, and given that the windy was true, if I assume that all of these are conditionally independent, isn't going to turn into this joint probability here. Instead, it's just going to be a product. It's just going to be the probability that it is sunny given I play tennis. Right, so I'm using this equation here. So A and B are all of these. A, B, given C, given our play tennis, is just going to be the probability, the product of those conditional probabilities here. So probability of sunny given play tennis, probability of humidity being high given play tennis, and then times the probability being windy being true, again given play tennis. And so that was all of our likelihood times the prior, of course, which is the probability of play tennis itself. Play tennis. So we're sort of now easily able to compute the probabilities of me playing tennis or not playing tennis given several attributes here based on just products of conditional probabilities. So no longer I'm using joint probability distributions going forward. And this is only possible, again, this is only possible when I'm assuming that my outlook, that my humidity, and my windy are in fact conditionally independent. And that's sort of a naive approach to go with, because it might be really possible that, let's say, the outlook really depends on how humid it is outside, or the nature of windy really depends on what the outlook is. And we already seen in the data set that the temperature is never hot when Outlook is rainy. So there are some sort of dependence going on or correlations in our data set, but if we assume that all of my attributes here are conditionally independent, then I'm able to convert these pesky, again, joint probabilities into just products of conditional probabilities, and it becomes really, really computationally feasible to calculate the probabilities of my class. And this whole idea that I'm using this notion that all my data and the attributes are conditionally independent, this is called naive Bayes. Let's write a more formal definition here. And so if I were to consider attributes A, let's do it in white, and they are basically A1, A2, all the way to AN. So in our case, this could be Outlook, this could be temperature, this could be humidity, and so on and so forth. And we also have a target class, C, and these are our attributes here. Then in that case, if I were to assume, so if we assume that all AI are conditionally independent, given, so we're still using conditional probabilities here, given C, so given some class, then we can create a naive Bayes classifier. And again, the idea is that the probability of some class given all of these, so A1, A2, all the way to AN, is more or less equals to the probability of A1, A2, all the way to AN given my class. That's the likelihood times the probability of my class. That's the prior. And we know that if we're assuming that all of these are conditionally independent, then we don't need a joint probability here. Instead, we will assume that it is a product of I equals 1 to n of all of my AI given a class. So this is me using naive Bayes times the product of the class, and I'm going to put box brackets around here. Okay, so it's much cleaner here. Also note that this guy here, so this equation here, is going to be using a product of pretty small probabilities because you're going so much in depth. So I could have so many different attributes here. You might be really close to values that are 0, closer to 0, not quite 0. In that case, if you remember, what we can do is we can use the log of these values. So to avoid the underflow, if we have too many near 0 values and only a couple that are big probability values, to avoid that underflow, we will log transform. So we're going to take this part and we're going to convert that into, so just this part, we're going to convert it into the summation. So if I take the log, the product turns into the summation of log of the probability of AI given a class times, well, log will convert that product into addition plus the log of my class here. And again, this is only if you know that you're going to be playing around with probabilities that are going to be really small. So if they're really close to 0, multiplying tiny values together is not a good idea. So we're just gonna not come to the point where it becomes so small. So let's say you get, I've seen that, you get, let's say get something lines of 0.0000, that like several zeros, 5, you might have a computer that might not go in that depth. So you might be playing with a programming language that does not have that many floating point storage in that case. So it will assume that this is all going to be 0. So if you want to avoid that, underflow, what you're going to do is take the log transformation. So everything is going to be a sum instead of the product. Now, given that we know that most attributes in real world data are not correlated, why would this trick make sense? Well, sometimes correlations don't really tell us a lot more information than just how two variables are basically correlated. So think of an example of the very commonly used example in terms of naive Bayes here is that if I'm able to classify spam emails, right? And so let's say you can say, okay, what is the probability that this email is spam, given that there are words Viagra, let's say, in there, and let's say Prince, and let's say free, right? Those are the most common things you'll see in a spam email. And so the appearance of Viagra alone will be enough to sort of convince you that it's probably going to be spam, right? But you don't want the complexity of a joint distribution. So instead, what you'll say, okay, I'm going to assume that there are conditional independence going on. So I might have an email where I have both Viagra and Prince, and you can then say, okay, there might be emails where Viagra and free show up a lot, but why go into the depth of, there is sort of correlation? Instead, why not just use those use naive Bayes to then say, okay, this is going to turn out to be, the formula is going to be the probability that there was a keyword Viagra in the email given that it's spam, and times it. So the probability that's going to be Prince given spam, and so on and so forth. So again, using this naive approach of saying that your attributes are conditionally independent is, again, is just basically going to create a set of calculations that are very easy to compute. You're not going to be using a lot of probabilities as you would with joint probabilities, and adding this log transformation also helps a lot. Now, there's also the danger of using naive Bayes, and whenever naive Bayes sort of predicts, it tends to be very confident because it is basically overcounting the amount of knowledge in highly correlated variables. Because we're assuming that everything is uncorrelated, if you were to use, let's say, BMI, height, and weight to predict a class using naive Bayes, it's going to give you very huge accuracy scores, because it will be unable to sort of realize that BMI is depending on height and weight. So in that case, naive Bayes might overperform, and so usually the idea is that you assume conditional independence when you know that a variable is not a derived version of another variable. And we'll also see some other examples in class.